ODP 207, fine. So most people discovered it was basically a single line of code. So that was really just kind of practice on manipulating pointers. First practice on it. So so I've put ODP 208 on the server, but it's going to open tomorrow morning at 8. So you can read it ahead of time if you want. And I want to talk about it today, but I'll post it on Canvas and it'll actually open up tomorrow morning at 8 and will be due 24 hours after that. So 208, you're building a linked list manually. So you're going to make a function called build. I'm going to pass you 3 integers, and you're going to make a linked list of 3 nodes and a sentinel. And your list will look like my fancy ASCII art, which was fun to make. So sentinel node, which I'm calling list, I don't care what the data value is. The next field should point to another struct node, which has a data value of x and points to another node with a y, points to another node of z, and that third node should have a next pointer of null. So you construct this list and you return as the function value the address of that sentinel node. So this is what you might do in your main program. If you're working on your print program, you need a list to practice on, you would build a list. So do some mallocs, set up your data fields, set up your next fields, and then return a pointer to that first sentinel node, so the address of the sentinel. It'll take more than one line, but it's really just 4 calls to malloc and then a bunch of assignment statements. Okay, so your function is called build. Here's the prototype for it. Takes 3 integers, returns a struct node pointer. The test bed is main208.0, which doesn't exist yet, but will exist this afternoon. But you can start writing this function yourself, and then tomorrow morning you can assess it, and it should be pretty straightforward. Okay, you're not sorting your nodes. Okay, if I pass you x, y, z, build x, y, z. If x is bigger than y and z, don't worry about it. So this is not your add function. Okay, this is just manually cobbling together 4 nodes and having them linked in this way. Is that clear? Okay, it's easier than the add function. But I've asked this question on exams before, and the majority of people weren't able to do it. So, good practice. All right, and then Monday morning I'll post some more. I'll post a new ODP, and I'll post a few of them next week, and I'll have you start doing things like deleting nodes and inserting nodes, and so on. So again, it's just kind of practice with working with these pointers. Yeah?
I have a question.
Okay.
I feel like I'm going to the file, like get the file, but I couldn't find any main -208.
Yeah, I said it doesn't exist yet.
Oh, yeah.
Right, I'll put it up there this afternoon. So this assignment isn't actually live until tomorrow morning. But if you don't come into class tomorrow, right, I wanted to talk about it today. Yeah?
Is there, do you have to worry about them being similar? No, that's the thing you want us to do in PA2.
What about them being similar?
If X and Y are the same.
Nope, you're just building X, Y, Z. Whatever I give you, that's what you put in.
Okay.
Right? So no relation to PA2 per se.
So this is due Saturday morning?
This is due Saturday morning, yeah. Opens up tomorrow morning. So you can write it ahead of time, right? Because you got the full specification. You can write your own main code. And if you've already gotten your print code written, right, you can test it out on this. And then Saturday or Friday morning, you can just link it up, assess, we're done. Finished until Monday. So I want to talk about, so no other questions? How's PA2? Have you started making progress on it? Cool.
So I guess this might be something we talk about in after the class thing. I have a weird error where it creates, according to the thing, my first node I create always doesn't create correctly.
Okay.
Doesn't free correctly. But it works just like I think it should.
Okay.
Visually, it looks okay. It
Okay.
Whatever it is, the thing beyond setting.
Yeah, if you can come by office, we can go through your code. So I have hours today at 12 o'clock till 1. And then tomorrow from 12 to 2, I think. So yeah, remember, I'm going to post a note on Canvas to remind people, but remember at the end of your program, you need to free all the memory that you allocated. Right, so one way to do that is to just delete every node and then call free. But a better way to do it is just to go through your list and free things behind you. Right, so start with sentinel. Right, pretend you're doing your print. So start off with your temporary node here. Well, copy that into some other location, change temp to be that node and free save. And then copy temp to save, move temp to the next node and free save. And then copy temp to save, move temp to the next node and free save. So march down the list one last time and pick up the blocks behind you, right? Send them back into the heap. And when you're done and temp is finally null, free that last block and you should have all your memory released. Alright, so variations on linked lists. One variation is a circular list. And a circular list, you can probably imagine, the last node, instead of being null, points back to the beginning of the list. And with a sentinel node, we could point back to the sentinel, or we could point back to the first node of the list. I'm going to think of this as not having a sentinel node, so for simplicity, I'll just point back to the very first node in the actual physical linked list. And so the idea of a circular list is if you keep following links, you're not going to get a seg fault. You're not going to get to a point where the next node is null and you try to look at that thing's data and you seg fault. But on the other hand, if you don't do something to stop yourself and you try to print and you just keep following nodes, you're going to print out forever, right? Because it's circular. So why would you want to do this? It can take care of edge cases, but it can also let you sort of work through this list in order without having to start back from the beginning. So suppose you want to read a node out of your list and then do some processing and then read the next node, right? So you could read this node and then save a pointer to this node somewhere, do some processing, come back, read this node, save a pointer to this node somewhere, and when you get to the end, you can just keep going. Okay, so we wouldn't do this if we had stored some data in here and we just wanted to read the data out. But if we're using this as part of another structure, and we want basically an array that never ends, but isn't actually infinite, we can use a circular list. As long as we're removing things from the array before we insert too many things, and we don't actually delete the node, we just somehow mark it with a flag as not being in use anymore. So we can fill up this, and we can fill up this, and we can fill up this, and then we start emptying these things out, so maybe this is empty and this is empty. And by the time we fill up this one, we might have a few empty nodes here, we can just keep going and fill up this and fill up this. And we'll see ways to use this next week when we talk about queues. So next week we're going to talk stacks and queues. And this is one way we can implement a queue is with a circular list. And it's a little easier than doing an array. So that's one variation, and it takes very little change to what we've been doing. It's just a convention that our last node, instead of being null, is going to point back to the beginning. So that's not terribly different. Let me show you one that is a little more different. So this is a doubly linked list. So the idea here is to change our basic node structure to have three pieces. So the first is our data. The second is a pointer to the next node, but we add a third field, which is the pointer to the previous node. So our links go in two directions now. Yeah, so you can go backwards. One of the problems with linked lists is the way we've been doing them, you can only move forward. So if you want to find some piece of information, you got to start from the beginning and go forward to the end. But sometimes it might be nice to move in the other direction. So here's some data, and we can have a sentinel or we cannot have a sentinel. I'm going to do this without a sentinel, just because I don't want to have to worry about what to do with the sentinel. So here's our forward pointers. Same as usual. But our, oh, and this one's null. And then we have these back pointers that go like this. And the first node, its back pointer is going to be null. So one advantage right away is when we're writing our algorithms, we can get away with a little less housekeeping. Remember when we were looking to delete a node, we had to remember the previous node, so that when we got to the node we wanted to delete 40, we knew what the previous node was, so we could adjust the pointers. We don't have to do that here. We can just say, is this the node, is this the node, is this the node? Once we find this node, we have a way to get a hold of the node before it. We just follow the previous link, and that tells us what the prior node was, so we can adjust its pointers. So that's one advantage programmatically. Someone asked that yesterday, and I said no, and I've been thinking about it since. No, let's not do it for PA2. I'll let you do it after that. With PA2, let's stick to a singularly linked list with a sentinel. All right, another advantage of this is locality of data. If this is some big collection of data and we're trying to search for things or pick up information associated with certain keys, right, we might start at the beginning and move through and get to the number that we're looking for. Or imagine this list is 1,000,000 elements long, and we get 3/4 of the way through and there's the piece of information we're looking for. Okay, it turns out that in a lot of cases, the way that we write code, the way we store information, if we get a piece of information over here, there's a good chance we're going to want more information close to that one. Okay, this is locality of data. And if we save our pointer to this node, and now we come in with a new request, and it's only 5 nodes away, right, we only have to follow a link 5 times, whereas if we go back to the beginning in a singular list, we got to go through 750,000 nodes to get to the next piece of information. Yeah?
So with the circular node, do you need a sentinel?
You can do any of these with or without a sentinel.
Actually, thinking you could combine the two into exactly what you're thinking, and just wherever you left off, that's your new sentinel.
Yeah, so you could have this point to the first one, you could have this point to the last one. Yeah, you can make a circular doubly linked list. And then you got all the goodies. Good comment. So locality of data. Like I say, it turns out, for example, when you're a CPU and you're executing code and you're inside a function, usually there's a bunch of local variables. those local variables are stored close to each other in memory, right? Because they were allocated at the same time, so they're physically close to each other in the memory. And our architectures take advantage of this locality. That's what cache memory does. One of the things cache memory does is when you access something at this location, you usually pull in a whole block of data near that location and throw it into your cache. And the next time you access some different location, chances are it's in that block you already got.
Is that why it's like inefficient to use global variables?
That's one reason global variables can be inefficient, yes. It's also why if you're storing things in an array, it can be helpful to know how that array is stored in memory. Is it stored going across each row, or is it stored going down each column? And if you get it wrong, you can see a serious impact on your performance, because you get what are called cache misses, or worse yet, page faults, when you try to access what looks like sequential locations, but they're actually far apart in memory. So this is part of where computer architecture and hardware design and programming kind of meet, and it's why we can't just learn to program without also learning computer architecture and assembly language and all this other stuff, because it all affects everything. So we can take advantage of locality. Now there's a downside to a doubly linked list, which is your code gets a little more complex. So let's say we want to delete 40. And let's say I'm calling this temp. So how do I have to change my pointers?
You have to set the next of the previous, and then set the previous of the next.
Okay, you have to set the next of the previous, and you have to set the previous of the next. So the next of the previous should skip over temp and point here. And you can do that by saying temp, arrow previous, arrow next. So this is the thing pointed to by temp. This is the address of this block is temp. Temp arrow previous says look at the thing that this is pointing to, pick up the previous field. That's the address of the 20. That address arrow next is saying go to that location in memory, that's the 20 node. Look at the next field. So this right here is temp arrow previous arrow next. And we want to set that equal to whatever temp was pointing to, which was temp arrow next. And that sets up this blue link. Yeah?
Can I use the two of arrow at the same time?
What do you mean at the same time?
Like usually I just use a temp arrow previous, but it's a temp arrow previous and arrow next.
Like this?
Yeah.
Yeah.
Okay.
That's exactly how you write it actually. And then the back pointer, we need to change this and have it point back at the 20. And so that's temp arrow next arrow previous equals temp previous. So this is in the category of things you don't want to try to memorize those two statements. Okay? You don't want to put them down on your cheat sheet for an exam. You want to understand how these statements do this, right? Well, first you want to understand that this is what you want to do. Change that arrow to that. And then understand that this expression gets you this, and this expression gets you the address of this block. And so you're just setting that to point to that block. Okay? When you can grok this, when you can wrap your brain around this and internalize it, right, the struggle's over. The rest of the course is really straightforward. And some of you are already here, most of you are already close to this point, right? So it's practice, it'll click. And when you can write this and use that to say take temp, go to the next, and then go to the previous, right, it becomes very sort of automatic. to do all the kinds of things we're going to do with data structures from here on out. And if you don't like this, here's a different way to do this. Right? We could say previous equals temp arrow previous. And now what I'm doing is I'm making a struct node pointer that points to this block. And I could even say, you know, next equals temp arrow next. And now I'm making another struct node pointer named next that points to this block. And now I just do my PA1 or PA2 and I say previous arrow next equals next. So I take this block, I set its next field to point to this block. And if you want to spell it out in 3 steps like this with temporary variables, nothing wrong with that. Right? But then at some point you can realize that previous was just temp arrow previous, and so I could have just said temp arrow previous instead of this temporary variable, and this becomes temp arrow previous arrow next. And over here, instead of next, I could have just said temp arrow next, and that's where the statement comes from. So break it into pieces if you like, and then think about just the fact that you could put it together in a single statement. Alright, so that's doubly linked lists. And adding a node is even more complex, because when you want to insert a node, you got to do 4 things. So right now this point's here, and this point's back here. So let me put some values in here. So if you're inserting a new node, let's say 15. Well, you need to change the previous node's next to point to your new node. You need to set your new node's next to point to your previous node's old next. You need to change the next node's previous to point to your new node. And you need to set up your new node's previous to point to your previous node, and leave all the other pointers the same. So now if we're following forward, we got to the 10, we go to the 15, we go to the 20, that's PA1. But if we're following backwards, we come into the 20, we go back to the 15, we go back to the 10. So you'll have 4 virtually looking assignment statements in there. But logically, it's no different from using a singly linked list. Okay. All right, so what if there's no sentinel? So I want you to use a sentinel for PA2, okay, same as PA1, but I want to look at what happens if we don't have the sentinel node in there. And it makes some things easier, but it makes most things more difficult for linked lists. But when we move to binary trees and other structures, we're going to get rid of the sentinel. Okay, it's almost a little bit like a crutch. It makes some edge cases go away, but eventually we'll do away with it. So let's look at a list where we don't have a sentinel node. So, and we're back to singly linked lists now. So 2 data nodes, a 10 and a 20. and there's a null. So this is 2 nodes. And we call our, let's say we're calling our list by the variable list. So list is the address of the first data node, which has a 10. That block points to a second data node, which has a 20, and that has a pointer of null. Okay, if you have 1 node, what does this look like? List is right here, data value is 10, next value is null. If you have 0 nodes, what does our list look like? That's it. It's just empty space. But what is list equal to? Because list is the address of the first data node. If we don't have a data node, there's nothing for us to have the address of. So list has a separate meaning in this case. We actually set it to a value that cannot be the address of a node. It's a flag. When list is equal to null, that tells us the list is empty. And we need to know that, because if we say, let's look at the first data node, show me list arrow data, that's a seg fault. Because list arrow data says go to the address in memory that list is, and list has a 0, that's the value of null, and memory location 0 is not readable. So that'll seg false. So wherever we're working with a list, we have to check to make sure it's not empty first. With Sentinel, we didn't have to do that. We had to check for null in our while loop so we don't run off the end of the list, but we always just started with that while loop. We didn't have to check this special case where there's nothing in the list. So that's one complication if you don't have a Sentinel. Alright, so remember, list is a pointer to a struct node. And let's think about our add routine. So our add function takes a list and it takes an integer. So I'll just pick an integer like 10. And it says, let's add this number to the linked list. Okay, this was the prototype of our add function in PA1 and PA2. It takes a struct node pointer, it takes an integer, and it doesn't return anything. And it inserts that number into the list. Okay, well, if I'm, adding 100 to this list, which already has 2 nodes, my routine will go through it, look at the 10, look at the 20, 100's bigger than all of those, it'll make a new node. This null will point to that new node, the new node will have a next of null, and I'm done. I've added my new node to the list. No different from what we've been doing. But if I try to add the number 10 and my list is null to begin with, something different is going to happen. Because if list is null, so if no nodes, no nodes are present yet, list is null. So when I try to add my first node, here's what I'm calling from main. I'm saying add null, comma 10. And in my add routine, I'll look at that first argument, which is the address of my first node. I'll see that it's null. I say, aha, I have an empty list. I'll malloc a node. I'll store a 10 in there, I'll set the next to null, and I'll return. When I return to add, what's the value of list now? It's still null. You can't change the value of a variable in C that you pass to a function. Everything's always passed by value. So if I make a loop that says get a number from the user, call add, pass the list, pass that integer, and I hope that I'm going to build up a linked list of these numbers. When I come back and I look at my list, it's still going to be equal to null. I've still got an empty list. I created a bunch of nodes in my add calls, and I did something with them, but they have nothing to do with the list that I passed in. And the problem here is that list somehow needs to change from being null to being the address of that struct node that was created. And if I just pass list, that doesn't happen because it's passed by value. So I could pass the address of list, and now I've got the address of a struct node pointer, and that's kind of a nightmare. So probably what I need to do is I need to change the prototype of my function and have it return a struct node star. So struct node star add. And it takes a struct node star pointer, which is a list, and it takes an integer, which is a number. And now when I want to add something to a list, I have to do the following. I have to say list equals add list, comma 10. And I'm doing that just for the one special case where my list was empty to begin with, or where I'm inserting something before what's currently the first node. Because here's the other possibility. It could be that my old list was this, and I add a 5, and so my new list looks like this. Well, before I added, let's say this node was stored at location 240 hex. And let's say this node is stored at location 280 hex. Well, before I make this call to add, list is 240 hex. It's the address of the first node in the list. After I come back from this call, I somehow need list to be equal to 280 hex. Because the first node of the list has changed, and list is always supposed to be the address of the first node. And again, if I just say add list comma 5, list is going to have the same value when I come back as it did when I went in. You can't change the value of a function argument in C. So I would need to say something like list equals add list comma 5. And then my add function in this case would return a 280 hex, and now list is pointing to that first node. So we've always got to be passing back these values in addition to passing them in. And we have the same kind of edge case if we delete the first node. The thing that we're using to refer to the first node of the list has got to change value. So deleting the first node, inserting before the first node, or inserting on the end of an empty list all need to change the value of what our list variable is pointing at. So you need to return pointers and use those in your main code. And most of the time when you say list equals add list, list is going to have the same value that it started with. Right? It's just if you add in the beginning or delete in the beginning. And then we also need the special edge case check anytime that we work with a list. For example, in your search, first thing you have to do is say, is the list null? If it is, return not found. Otherwise, you can go into your while loop and start searching for the actual data value. So the sentinel node gets rid of all of that, for the simple reason that there's always a first node and it never changes location. Okay, that's why we use sentinels. So any questions about that? Sentinels are handy, they're cheap, right? It's one extra node. There's not really a downside to them. but we can't use them when we start doing trees because they screw up your recursion, and we're going to be doing everything recursively. So we'll get rid of sentinels, and I just want you to sort of see a first view of the kinds of things that we're going to have to get used to when we don't know that there's always a first node present. But we'll talk a lot about that when we get there. So when I say you can't change the value of an argument in a C function, is that okay with everybody? Because we use scanf to change the values of variables all the time, right? So how does that agree with what I just said? Right, we do this, buffer is a string containing, the character 3, and when I come back, n's been changed to 3, right? But n was not the argument to scanf, the address of n was the argument. And scanf cannot change the address of n, but that's not what we're doing, right? We're passing in a number, which is the location in memory where n is stored, and it's using that number to go into memory and write a value. So when we come back and we say n, we look at that same location in memory, there's a different value. But we're not actually changing the value of this argument, right? We're using it to do indirection. But C is always passed by value in the end. You pass a number, and that number can't be changed so that when you get back to your caller, it's got a different value. You can't do that. All right, so any questions on any of that? We're going to change gears here. So keep working PA2, keep asking questions, come tomorrow and work on it in here if you want, and I'll be available. But I want to shift gears now and start talking about what's coming up next week. So next week, stacks and queues. So a very different data structure from a linked list. We're back to looking at fundamentally different ways to store information. That might be useful. A linked list is useful if you want to store information and say keep it sorted and be able to squeeze things into the middle or remove things from the middle without having to shuffle everything around in an array. Okay, so that was one of our motivations for linked lists. Stacks and queues do something very different. They're useful when you want control over the order in which you retrieve information that you've previously stored. And they're kind of duals to each other. So let's talk about stacks first. So here's the way that I was taught stacks way back when. You go to a Chinese restaurant, you go up to the buffet, and there's all the food there, right? So what's the first thing you do when you get to the buffet counter?
Sit down.
No, it's a serve yourself kind of buffet counter. Grab a plate, right? So they got that pile of plates there, and you take a plate off the top, and it's sitting on top of some kind of spring-loaded mechanism, so once you take that plate off, the whole pile moves up and there's another plate sitting there for the next person to take. Right? So if you haven't encountered this, just sort of imagine it. Okay, that pile of plates is basically a stack. It's a stack of plates. And it has the following characteristics. You can only take from the top. And that's true because there's only one plate sitting above this cylinder that has all the plates in it. But of course you take the first plate and it's wet and you don't want to use that. So you grab the second plate and you put the first plate back. Right? So you can get to the second plate, but you can only get to the second plate by taking off the first one and then taking off the second one, and then you can put the first one back. So we only take from the top, and it turns out we also only put to the top. So when you want to add plates to the stack, you always have to do it from the top. And when the dishwasher comes out with a big stack of freshly washed dishes and wants to put them in the supply, they take it and they put it on top of the entire thing and it pushes everything down. Basically what they're doing is they're taking one plate, putting it on top, put another plate on top, put another on top, and it keeps pushing down. So all the access is done through this one end of the stack. And you can't just sort of go in and grab a plate that's 20 dishes down. Okay, that's very stack-like. Another property of the stack is that the last plate that gets put on that stack is going to be the first plate that gets taken off. Right, so you might come out with 5 plates and put them down on top of the stack. That last plate you put on, that's the first one that someone's going to grab when somebody takes from the stack. So we call this last in, first out. And we abbreviated LIFO. So a LIFO is almost another term for a stack.
Sounds exactly like the stack in 270.
Say what?
Sounds exactly like the stack in
It is exactly like the stack in 270, without the Chinese food. All right, so last in, first out, or first in, last out, if you like. It's usually called LIFO. Now, if you try to pile too many plates on the stack, right, each time you put a plate, the stack gets heavier, the spring compresses more, and everything moves down further. But it's not an infinite hole in the earth, right? It just goes to the bottom of the cart. So once you fill up the stack with plates, you can't put any more plates on. Well, you can balance one more plate on top, but it's probably going to slide off and break, right? So your stack can become full. And then if you try to put one more plate on top, you get what's called an overflow. So your pile is overflowing. So stack overflow, that's where the site comes in. The other thing you can do is you can start taking plates off the stack, but once you've taken the last plate, there's no more plates left. And if you try to take one more plate, you'll fail. So that's called an underflow, which is trying to take from an empty stack. So if you try to add to a stack that's already full, you get an overflow. If you try to take from a stack that's already empty, that's an underflow. That's the essence of a stack. Okay, and we're going to talk about how to implement stacks in code. And our plates are probably going to be integers for what we do, but they could be anything. Anything that we can store in some kind of list or array or something. And when we design a stack, we're going to stick to this notion of adding to the top, removing from the top. So taking from the top, we're going to call that a pop. And putting on the top, we're going to call that a push. Some more 270 references. Anybody here play Magic? You ever play old Magic with like interrupts? So that's a Magic concept. So current Magic, right, there's a stack. When you put effects down and you want to resolve them, you pull them off, last one first. It's basically a stack. So they even use that terminology. That's how I got into Magic, because I was teaching stacks in 270 and my students were whispering. I'm like, question? They're like, no, we got it now. So I asked them what they were talking about, and they said, oh, it's just like, you know, you put cards down in Magic. So, all right, so that's stacks. The dual to that is a queue. Okay, and the thing to keep in mind for a queue is, think of the checkout line at the store. So there is a line, and it's just a single cashier, single line, and you come up to the line, and somebody's in the front of the line being serviced. There's somebody behind them, they're the next person who's going to be serviced. Someone behind them is going to be next. And then there's you, and you're going to be serviced after those 3 people are done. And if somebody comes in behind me, they're going to be taken care of after I'm done. So the image is you come into this queue, and there's the first person, second person, third person, fourth person. And that's the same order in which they're going to come out of the end of this queue. So the first person in is the first person out. So this is called a Fifo. So a stack, you kind of process things in the opposite order in which they arrive. The last person in gets the first service. In a queue or a Fifo, the first person in comes out first, the second person in comes out second, the last person in will come out last. So it's kind of a dual to a stack. It's not really opposite, but they're similar.
Is standard in a queue?
Standard in you can think of as a queue, right? Because the first character you typed is the first character that F gets will read, right? Or F gets C. So FIFOs are much more sort of common in our experience, right? Not just in checkout lines, but anything where you're queuing things up, right? So it's in the definition. And queues can become empty, right, if there's nothing to serve. And in reality, they can become full in practical terms. So when the checkout line gets back to the end of the store and it's wrapping around, there's no place to fit anybody else, right? Then your queue is full. You can't let anybody else come in line until somebody comes off the front. So we'll have full queues and empty queues to deal with, just like with a stack. And we only insert into the queue at the back, and we only remove from the queue at the front, right? Otherwise, you're line jumping. So you're not allowed to come in here and suddenly a fifth person comes along and jumps in here. That's not a queue anymore. All right, so that's the general idea, just to sort of think about until Monday. We'll start going through stacks in some detail. We'll look at implementations of them, and then the second half of the week we'll do the same for queues. And I'm pretty sure PA3 is going to be stacks and queues, so you'll get some coding practice. All right, cool. I will see you next time.